All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus, Unit 3, Section 4. Section 4 begins on page 58 and it's titled Radian Measure. It says one system that is often used in trigonometric applications is based on geometric relationships between a central angle of a circle and the arc it intercepts. Radians, or what these are called, measure is considered a more natural way of measuring angles, right? So it's just a different way of measuring angles than degrees, okay? So here is what a radian actually means. It says that a central angle has the measure of 1 radian if the angle intercepts an arc equal in length to the radius. So the arc that it's intercepting, which is AB right here, is equal to the radius of the circle. So therefore, this makes a central angle, of course, and then we have a radian, okay? From geometry, you know that the circumference of a circle is C equals 2 pi r, or C equals diameter, right, times pi. And it says since a unit circle has a radius of 1, the circumference of a unit circle is 2 pi. And that is our radians. So 1 time around the circle is 2 pi radians. Okay? And there are 2 pi radians in any circle. It asks the question, does that work for every circle? Well, yes, it does. Okay? Regardless of the size of the circle, okay? 2 pi is the radian measure of the whole circle. So it is independent of the size of the circle. And just as there are 360 degrees in every circle, no matter how large or small, there are 2 pi, or about 6.28 radians in any circle. 2 pi would be the exact measure. 6.28 would just be an approximation, okay? Now, as we keep going here at the top of this next column, it says the radian measure of a central angle is theta, or central angle theta, is given by the following formula. Okay, so this formula is important. Theta is equal to the arc length divided by the radius. And of course, this formula can be manipulated to solve for any part of this, right? But this is the formula that we're dealing with, and here's the legend to explain it, right? Because these are letters we probably are more comfortable using for other things maybe, but R for radians is pretty natural. S for arc length is probably something new for you, okay? But that's what it means. Here's our example. Find the radian measure of a central angle. Okay, so we're looking for the radian, which is theta, that intercepts an arc of 10 centimeters, so the arc of 10 centimeters, on a circle whose radius is 4 centimeters, okay? The radius is 4 centimeters. So we're going to use the formula, theta equals arc length over the radius, 10 over 4, divide 2.5 radians, okay, is what the answer is. And then they have this think about it square with the circumference here, right? Because the radius is 4, the circumference of the circle, this particular circle they're talking about, is 8 pi. And so it makes sense that if you went 10 centimeters, that it would be less than halfway around the circle, okay? Or 2.5 radians. All right, so they're just having you think about it in a different way, but we're just using the formula that they provided, okay? All right, let's turn the page. The example at the top of page 60 reads, find the length of the arc intercept by a central angle of pi radians on a circle whose radius is 9 inches. Okay, this time they didn't give us the S, right, the length of the arc, but they gave us everything else. The other two pieces, right, they gave us the pi radians, which they put here, and they gave us a radius of 9. To solve for S, you simply multiply both sides by 9. So S is pi 9 pi in length. The arc is 9 pi in length, or approximately, because anytime you use 3.14 for pi, you're rounding, right? Approximately 28.3 inches. Okay? Pay attention to the instructions, whether they want the exact answer or not. Okay? If it doesn't say, I would assume it wants an exact answer. Okay? Moving forward, here we go. The next part here reads, looking at the terminal side, there are 2 pi radians in a circle, and there are pi radians in a semicircle. So here we go. If we're traveling around, we've gone halfway around the circle, we're at pi, and we've gone the other half, we are at 2 pi, okay? Now, obviously, if we're halfway, or sorry, a quarter of the way, but halfway to pi, then it's pi over 2. And if we are 3/4 of the way, or 3 pieces, right? If each piece is pi over 2, this is pi over 2, this is pi over 2, this is pi over 2, then we get to 3 pi over 2 here before we finish our circle, okay? All even multiples of pi can be reduced to 0 radians. 0, 2 pi, 4 pi, 6 pi, so on and so forth. All odd multiples of pi can be reduced to pi radians because the odd ones are landing over here, okay? Multiples anyway. All right, so here is our terminal side circle that we're going to be working with. And of course, there's all kinds of things that fall in between. Here it says, for this example, determine the quadrant in which 5 pi over 4 terminates. Okay, well, 5 pi over 4, they've changed it over to a mixed number, 1 1/4, or 1 and pi over 4, right? 1 and pi over 4 is going to get us here because 1 pi gets us here, and pi over 4 gets us down here somewhere, right? And so we terminate in the third quadrant. Example, this next example, determine the quadrant in which 5 pi over 6 terminates, okay? Well, 5 pi over 6 isn't 1, right? We're not making it all the way to pi because this isn't 1. It's less than 1, but it's more than 1/2, because remember, looking at our circle, 1/2 pi is here and regular pi is there. So it's going to fall somewhere over here and in quadrant 2. Okay? Now, of course, since we've learned a new unit of measure, we have to learn how to convert this unit of measure. Okay? And that's what this next part is. It says here there are 360 degrees or 2 pi radians in a circle. Therefore, 2 pi radians equals 360 degrees, or just to make it a little bit easier, pi radians equals 180. So no matter which way you're going, here is our conversion. Looking at the examples here at the top of the page. Convert 120 degrees to radians. So we set this up like a conversion. We are given 120 degrees. So our degree measure needs to go in the bottom of our fraction that we're going to multiply by, and then the radians in the top. Therefore, our degrees cancel, and we're left with radians, or pi, right? And then we simply reduce our fraction, okay? Basically division, but we're reducing our fraction. 2 pi over 3. The next example, convert 210 degrees to radians. Same thing. We have radians, so our degrees, we're given degrees, so our degrees go in the denominator. The thing that we want, radians, is going in the numerator. Our degrees cancel, and we're left with radians. They reduce. Make sure you're reducing as much as possible. The more we do these, the more you'll get accustomed to what reduces to what, okay? This example here, convert 5 pi over 3 radians to degrees. So now we have 5 pi over 3, but we want degrees. We're given pi, so our pi is going to go in the denominator. The thing we want, degrees, is going to go in the numerator. Our pi's cancel, And then we can just take 5 times 180 divided by 3 to get 300 degrees. Okay? Last example over here at the top of page 61. Convert 7 pi over 12 radians to degrees. Again, we set it up the same. Since we were given radians, our radians are going to go in the denominator, and our degrees, which is what we want, is in the numerator. We cancel our pi. 7 times 180 divided by 12 is 105 degrees. This note is kind of important to go through. It says when using radian measure, RAD is used as an abbreviation to distinguish it from degree measure, but expressions involving pi imply radian measure. The radian is really dimensionless by definition because the radian is defined to be the ratio of arc length over radius, both measured in the same unit. The units divide out. Okay, so if you are writing it, where was the example? Or over here, right? 28.3 radian inches, or inches radian, right? I guess it's inches now and not radian, but when they ask for radian measure, we just need to make sure we're using radian. Most of the time, we're just going to use the exact answer, so you don't need to write RAD or radian. Okay, so that's what they're saying here. Radians don't really have a unit of measure. Here we've changed it over to a unit of measure because we're solving. They wanted to know, find the length of the arc. You could have just left it as 9 pi instead of inches, but either way, we shouldn't have to mark it as a radian. It's implied by the pi symbol. Okay, let's take a look at a few of these problems together. Find the arc length intercepted by a central angle of pi over 2 radians in a circle whose radius is 24 inches. So remember, theta is the radians, right, is equal to the, we can call it the side, but it's like the arc length over the radius, okay? So if we know that the central angle is pi over 2, and that is equal to the size of the arc, this S really throws me off, sorry, the arc length over the radius. We're going to multiply both sides by 24 because we're trying to get S by itself, okay? S is equal to, we can reduce this to 12, so 12 pi, which is letter C. All right? Just using the formula is what we've been given. Let's turn the page. Let's take a look at number 4. In what quadrant does the angle 7 pi over 3 terminate? Well, 7 over 3 is the same as what, right? Let's change it to a mixed number, right? 3 goes into 7 twice, and there is then 1/3 left, okay? So this circle, or this angle, goes all the way around to 2 pi, okay? Because that's what we have here. Remember, this is a pi at the end here. And then it goes 1/3 more. Remember, this is pi over 2, or 1/2 pi, so it's not quite reaching there. And so it's going to be in the first quadrant, A. All right? Let's look at another one of those quadrant problems. In what quadrant does the angle 11 pi over 4 terminate? Well, let's do it again. 11 over 4 pi. 4 goes into 11 twice. This time there's 3/4 left. So we're hitting that 2 pi mark, right? That's what this 2 pi. And then we're going to 3/4 pi. If this is 1/2 pi and this is pi, we're not quite making it to pi again. We're going halfway in between 1/2 and pi, so it's going to be in the second quarter. Okay? All right, let's take a look at number 7. Number 7 says, express the angle in radian measure. 18 degrees equals what? Well, remember, theta equals, or no, I'll write that down here, but we don't need that one, right? arc measure divided by the radius. This one we're doing the conversion where pi is equal to 180 degrees. Okay, pi radians, 180 degrees. We've been given degrees. We're going to multiply that so that our degrees are in the denominator and our pi is here. So our degree cancels and we end up with 18 pi over 180. They have something in common, and it's an 18, right? 18 goes into 18 one time, and 18 goes into 180 10 times. So pi over 10 is our answer. Letter B. Let's do another one of these. Number 8, express the angle in radian measure, negative 135 degrees. Okay, so we're given a negative 135 degrees. So our degrees need to go into the denominator and our radian in the numerator. It's the only way our degrees will cancel, right? So we have negative 135 pi over 180, right? Our degrees are now gone. Now to reduce these, we have to start thinking about the angles, okay? Now you could obviously divide it by 5 and keep going until you found the correct answer. But let's think of it in the idea of our angle measurements, right? We have a common 30-degree angle and a common 45 and a 90, right? These are all 60 degrees. These are all special angles in, our unit circle or trigonometry in general. So let's use that when we're thinking about this. So I don't know if you can see my calculator, maybe right here. Okay. So I'm going to take 135. I know 30 doesn't go into it because it ends in a 5. It's just not going to work. So I'm going to take 135 and divide it by 45. And I get 3. Okay. I know 45 is going to go into 80 or 180 because that's how these things work. 45 is half of 90, 2 90s go into here, so there should be a 4. Okay, so remember, these all kind of build upon each other. So 3 pi over 4, negative, because we had negative here, right? So answer C. All right, so when you're doing these, of course, you can go piece by piece. You could have divided it by 5, and then 3, and then whatever, till you got to 45, right? But if we think about it in our angle measurements, our special ones, 30, 45, 60, 90, right? It'll be probably a little bit easier. Okay, let's take a look over here at problem 13. For problem 13, it says convert 5 pi over 12 to degrees. Okay, 5 pi over 12 to degrees. So this time the degrees are going to be in the numerator. And because we were given radians or pi, then our pi is going to be in the denominator. That cancels it out. And we're left with 5 times 180 degrees divided by 12, which we can just put in our calculator very easily. I shouldn't have put it away. And so we're going to take 5 times 180 and divide that by 12. And we get 75 degrees, okay? Let's do one more of those. Let's do this one here. 4 pi over 3, 2 degrees, okay? So we're given radians, so our radians need to be in the denominator and our degrees in the numerator. So then we can cancel, right? The only way we can cancel. So we're left with 4 times 180 degrees divided by 3. 4 times 180 equals, and I know I could do it all at once, but I don't trust my calculator that much. And that gives us 60 degrees. Okay, 60-degree angle. All right, so that's it for this part of this section. Go ahead and finish the problems we didn't do together and meet me back here for the next part. The next part of this section begins on page 64, and it's entitled Reference Angles, okay? The use of degree and radian measure varies depending on the application, but radians are more frequently used in calculus and the sciences. One reason is that they are fairly easy to substitute other measures such as length or time for radians. So looking at these reference angles, 30 degrees is pi over 6, which is approximately this, right? These are our special angles. Remember, 45 degrees is pi over 4, or approximately here, and 60 degrees is pi over 3, or approximately this. Now, based on that, they've set up a new chart, right? Remember, we were using the other chart. I think it's on page 37 maybe. And now they've updated it with our radian measure as well for us to be able to easily find our reference angles, okay? So note down here though, note, even though it is possible to convert the radian measure to degrees and then evaluate the trig function, this method requires more work and time. Try to work using the given radian measure. For our example, we have the cosecant of pi over 6. The cosecant is reciprocal of the pi function, or the sine function, oh my gosh, sine function. And the sine of pi over 6 is 1/2. If we go here to pi over 6, the sine is 1/2. Therefore, the cosecant of pi over 6 is 2, right? The reciprocal of it, or approximately blah, 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 0.5236. Not big on the approximation. I would have been fine with 2, right? Well, it's saying note that pi over 6 is 0.5236. If you put that in your calculator and did a reverse to-do, you'd be able to get 2. But let's not do that when we can just find the exact measure, right? Here it's saying evaluate the sine of 1.57. Now, in your radiant mode in your calculator, if I grab my calculator here, and they're not all going to be the same, but let me try to hold this up here. Let's turn it on. I'll check this one in a minute. Right here, there is a little d. That's what I normally work in, degrees. Then there's an R, and there's a G. I'm not really sure what the G stands for. I'll figure it out eventually, I'm sure. To get it to be R, which is radian mode, it's not just the mode. I wouldn't just click the mode. If we click mode, right, you'll see that radian is not there. There's a lot of things there. Radian is not one of them. But if I hit shift setup, which is what I'm into now, 3 is the degree that I'm in now, and 4 is radians. So if I hit 4, now I'm in, you can see that it went from the D to the R, okay? And that's where I'm at now. And that's what they want us to use for this problem. That probably wasn't super clear. Let's take a look at this calculator. So here on this calculator, if we turn it on, you'll see that it says DRG right here, degree, radian, whatever G is. Well, I guess we'll click it and see. GRD, whatever that, whatever this is. All right, but we want radians, so we would just move it over, and I assume hit enter, and now we're in radians. Now, here's the thing about switching your calculator. Don't forget to switch it back, because the sine of 1.57 degrees is not the same as the sine of 1.57 radians, okay? So don't forget to change it back when you're done and you're trying to do something else, when you're trying to do just regular math problems, because radians is not going to be the measure that you want, okay? So make sure when you're finished, you change it back to degrees, because that's just like the regular math page. Okay, so now that we're in radians though, and they want us to evaluate the sine of 1.57, which is literally 1.5, right? So the sine of 1.57 radians is 0.9999, right? Which is approximately 1. And this says 1.57 is approximately pi divided by 2. So it's the sine of 1/2 equals 1. Or sorry, not the 1/2. Pi over 2 equals 2. So if we take 3.14 and divide it by 2, I'm not sure. Okay, it'll work out. Okay, good. 3.14 divided by 2 is 1.57. All right. So again, that's something to look at when we're doing these problems, something to consider. All right. Okay. Example over here at the top of page 65. Evaluate cosine squared of pi over 4. Well, the cosine of pi over 4, right here, you can just barely see it, right? The cosine is square root of 2 over 2. And then you square it. The square root of 2 over 2 is, let's actually work it out. I mean, it becomes 1/2, but let's do the work. So we have the square root of 2 over 2, basically times the square root of 2 over 2, right? This is a 2, and this becomes a 4, and that's how they get to 1/2, okay? All right, so we have 1/2. Cosine squared of pi over 4 is equal to 1/2, all right? Also, working with radians, we can use reference angle to allow us to find the trig function parts, okay? So, remember reference angles. We learned them not that long ago. Those things apply here as well. If the angle is in quadrant 2, we subtract pi from the angle to figure out what the reference angle is. If the angle is in quadrant 3, we subtract the angle from pi. Quadrant 3, we subtract pi from the angle. And if the angle is in quadrant 4, we subtract the angle from 2 pi. Right? Sometimes I say, you know, how far past, how much farther till, you know, that kind of thing. But it's all just adding and subtracting. Okay? So let's take a look at the top of page 65 at this example. Find the exact value of the sine of 11 pi over 6. Okay? First thing it says is determine the quadrant the angle terminates. Well, 11 over 6 is almost, it's like literally 1/6 away from being 2, right? So we're over here in quadrant 4. They said rotate 1 full 6 over 6, right? 1 full pi is the 6 over 6, and then you have 5 over 6 left, right? But I like to think of it a little bit differently. You know, a full 2 would be 12 over 6, so we're 1/6 away, which ends up being our reference angle, right, is pi over 6, 1/6 away. So, and because this area here is the fourth quadrant, I forgot what we're looking for, sine, right? In this area, sine is negative. We have the negative sine of pi over 6, which over here, the sine, and we can't quite see it, of pi over 6 is 1/2. And so negative 1/2, and they wrote it as a decimal this time for some reason. When it says exact value, I guess 1/2 and 0.5 are exact values. There you go. I don't find this to be helpful, but go ahead and read it if you think it might be helpful. And then we will turn the page and look at some more examples. Top of page 66, express the tangent of 3 pi over 4 as a function of a positive acute angle. So it just means that we're going in the positive direction, okay? And then find its exact value. Okay, 3 pi over 4 is almost 1, right? If we were to think of it, where does it terminate, right? It's definitely more than 1/2, but it's not quite 1. It's over here. How much farther till it becomes 1 pi? Well, it's 1/4. So pi over 4, more to go, right? If we're talking about a tangent in this quadrant, quadrant 2, tangents are negative. So it's negative tangent of pi over 4. If we went back and looked, we would see that that's a negative 1, or a 1. So because ours is negative, it becomes a negative 1, okay? Now this little red box where it says this might help, we're going to try out. I haven't tried it yet, but I have my calculator in radians, and it says, in radian mode, let's just put this in. Tangent of 3 pi over 4, okay? So, I'm going to do it all at once. The tangent of 3 times pi surely there's a pi button here somewhere. And I found that pi button. I see that you can't really see. So I got the tangent of 3. The pi is right here. Okay, so I'm going to do shift and that button, 3 times pi divided by 4, close my parentheses and hit equal. Boom. The answer is -1. So that did work out for us. So that will help us in this. Although for this next example, it does say exact value. And if we put in this one in our calculator, because the answer is -√3/2, the calculator may not give us the exact answer. But let's see, the sine of 5 pi, so shift pi, divided by 3 equals. Okay, so this is definitely not an exact answer, right? Because I would have to round that, because it is rounded. It keeps going, I'm sure, forever and ever. Amen. So this is not an exact answer. So it's not always going to be helpful to us to put it into our calculator. But at least we see that we can put it in our calculator, okay? So for this one, right, we have to see 5 pi over 3 is the same as 5 over 3 pi, which is, what, 1 2/3 pi, right? We need to figure out where this falls. 2/3 is greater than 1/2, which is the 90 degrees, right? So it is over here somewhere, and it goes all the way around and then back to here, right? That's what our angle looks like. So we're in quadrant 2 where sine is positive, okay? So why did they make it negative? All right, I see where I made a mistake, right? We didn't quite get to 2. So it didn't go all the way around. So it went past the 1 pi, and then it went 2/3 of the way. So we are almost at 2, right? We are 1 pi over 3 away from being at 2 pi. That was my mistake. So we went past the 1, but we didn't quite make it to the 2, okay? So we are pi over 3 away from the 2. We're almost there. In the 4th quadrant, sine is negative. Back on the chart, the sine of pi over 3 is the square root of 3/2, but it's negative, so negative square root of 3/2. Okay? The next example here at the top of page 66, second column. Evaluate the cotangent of 7 pi over 2. Well, 7 pi over 2 can be written as 3 1/2. So again, in our circle, this is 2, this is 3, okay? And therefore the 1/2 ends us up right here. So this is 3 1/2 pi radians, okay? We're on the axis, and so the cosine, this is, of course, at 0, -1, right? So the cosine is 0, the sine is -1. So the cotangent is going to be 1 divided by 0, which is 0. Okay? And there we have it. We're done. So the answer is 0. Okay? It says, remember, use the coordinate of the points on the unit circle for the cosine and sine values of quadrantal angles. This is a quadrantal angle. All right, let's do some of these problems together. Which of the following trigonometric expressions is equivalent to tangent of 5 pi over 4? Okay, well, 5 pi or 5 over 4 pi is equal to 1 1/4 pi, right? So we made it past 1, but then we only went 1/4 of the way past there. So we are in this angle. We went 1/4 past our pi, or our 1. And so whatever this is, tangent in this quadrant is positive. And so we're at positive pi over 4, which is letter D. Okay. Let's do another one up here at the top of page 67. These reference angles should be, I mean, obviously we're getting used to a new type of measurement, but in general, these should be pretty understandable because we've been doing reference angles for a while. But let's take a look at a few more together, and then you could finish the rest on your own. For number 17, evaluate the tangent of 5 pi. Now, this is an odd number, right? This is 2 pi. This is 4 pi. This is 5 pi, okay? So we want the tangent of 180 degrees. Remember that the tangent is equal to sine over cosine, right? And so this value of this point right here is at -1, which is the cosine, 0, which is the sine. So this becomes 0 divided by -1, which we cannot do, and therefore is undefined, right? Evaluate the cosine of 11 pi over 6. Okay, this one almost makes it to 2, right? We get over here, but we don't quite make it. We are 1/6 or pi over 6 away from getting to 2, which is 1 full revolution. In this quadrant, our cosine is positive. So we have a positive cosine of pi over 6. Check your chart to see that is equal to the square root of 3 over 2. So again, with our letter D. All right, let's just do one more together. Evaluate the sine of 5 pi over 4. Okay. 5 pi over 4 is equal to 5 over 4 pi is equal to 1 1/4 pi, right? So we made it to the 1, and then we went 1/4 past it. So we're in the third quadrant, and we are pi over 4 past this line, this axis right here, right? Sine is negative here, so we are looking for the negative sine of pi over 4 in our chart, which is going to be negative square root of 2 over 2, okay, which right here is letter B. All right, go ahead and finish the rest on your own, and then meet me back here for the next part of this section. The last part of this section is about velocity, okay? Radian measure allows you to find the velocity of something that is traveling in a circular pattern. When objects follow a linear path, their speed is expressed as a ratio of distance over time, okay? Now, in this case, we're going to be using some different lettering, so it's important to make sure you understand this definition. Speed is when a body moves with a constant rate of motion. Rate of motion is v in time t. The distance s that the body travels is expressed by the formula s equals v times t. Solve the formula for v, and it gives you v equals s over t. S being the distance, so some of these letters are a little bit different than we're used to. But if you think about it in the last formula, right, where we had theta equals s over r, s was the distance, right, of our arc. It's the same thing here, okay? So the fraction s over t expresses average speed. Here's our example. The average speed of a person running 600 yards in 60 seconds is 600 yards over 60 seconds, or 10 yards per second. The average speed of a person driving a car that travels 250 miles in 5 hours is 250 divided by 5, or 50 miles per hour. So then we have our angular velocity. In the figure below, let P be a point on the circle, or here's our P, right? On circle O, that moves around the circle with a constant speed of v, okay? S will be the distance it travels in t amount of time. As point P moves on the circle with constant speed, the radius OP is generating a central angle theta. If theta is generated in t amount of time, then theta over t is called the angular velocity of point P, okay? So theta over t is the angular velocity, but the Greek letter omega, this W, is used to express angular velocity. So omega equals the radian degree, right, the central angle, divided by time. Okay, this is what we're going to be working with here. Going on to this next page, page 69. It says, it's possible to relate the linear and angular velocity of an object. Follow the steps to discover a relationship. So the formula for the linear velocity is V equals S over T. The radian measure of an angle is given by the following formula, what we learned in the last couple parts ago, beginning of this section, right? Theta is equal to S over R. So solving the formula for S, you get S is equal to theta times R. So then they take this S and they stick it in back up here, okay? So they substitute theta R into the previous equation. So now V is equal to theta R over T. They substitute omega, theta over time, okay? So they see how we have this is equal to theta over t times r, right? So they substitute the theta over t, the omega, and get that V is equal to omega times r, all right? All these pieces are coming together. Therefore, the linear velocity, or the speed, is equal to the angular velocity times the radius. Speed is equal to the angular velocity times the radius. Solving for the angular velocity, we get the angular velocity is equal to speed divided by the radius, okay? And it says, note, whatever formula is used, omega is expressed in radians, always in radians, okay? Looking at this example, a flywheel makes 120 revolutions per minute. What is the angular velocity in radians? Well, there are 2 pi radians in each revolution. Therefore, 120 revolutions per minute is equal to 120 times 2 pi radians per minute, or 240 pi radians per minute. Okay, so all they did here was multiply. Now, this next example is, I don't want to say it's more complicated, but I think they've made it more complicated than it needs to be. So we're going to look at how they did it, and then we're going to look at it a different way. Example here, top of page 69, second column. What is the speed in inches per minute of a point on the rim of a record? So like, let's say right here, 10 inches in diameter, turning at the rate of 45 RPM, or revolutions per minute. Now, 10-inch diameter tells me my radius is 5, right? So each revolution covers 2 pi radians, just like this problem here. Therefore, 45 RPM, or revolutions per minute, is the same as 90 radians per minute, okay? In 1 minute, the point travels an arc with a central angle of 90 radians, right? Or 90 radians per minute. Now they're using this formula that the velocity is equal to the angular velocity times the radius. So they've calculated the angular velocity at 90 radians per minute, and they were timesing it then by the radius, which is 5, to get 450 pi. That would be our answer, 450 pi per minute, but they're asking us for, what is the question? What is the speed in inches per minute? So we have to actually multiply it out, so it's not quite exact, right? 450 times pi is 1,414 inches per minute. Now, that is all fine and dandy. Not the way I would solve it, though, because our dot, our point, is on the outside, right? So when it goes one time around, it's going a full circumference, right? And the circumference of this record is 10 times pi, right? Or, I wrote it backwards for some reason, 10 pi. The rate, it's turning at a rate of 45 RPM, revolutions per minute. So in 1 minute, it's going 10 pi times 400 or 45, right? So this becomes 450 pi, which is where we're at here if we multiplied it out and we're done. So while this seems helpful, maybe in another example up ahead or one of the problems we work through, it would be more important to go at it or look at it in this way. I don't know that that was necessary for this problem because I feel like this was a little bit easier and we got to the same thing. Okay. So of course it's math. Sometimes there's more than one way to do the problem. So let's turn the page and do some of these together. On page 70, let's take a look at problem number 28. It says find the arc length intercepted by a central angle of 3 pi over 4 radians in a circle whose radius, so my central angle is this, and the radius is 18.4 inches. So this is our formula. Theta equals the arc length over the radius, right? So we have our arc length of 3 pi over 4 is equal to our theta is equal to 3 pi over 4, which equals our arc length divided by our radius of 18.4. We want to get S by itself, so we're going to multiply both sides by 18.4. They want it in pi, so I'm grabbing my calculator and I am taking 18.4 times 3 divided by 4. So I get 13.8 pi. Okay, so I didn't change it back to degrees. It seems to be working okay for just regular math sort of things. But again, when I'm done with this lesson, I will be changing it back to degrees because I don't want to get messed up in the future forgetting that it's on radians, right? So don't forget to change your calculator back. We'll leave it on there for now because I'm sure we'll be doing something with that shortly. Find the radius, number 29, of a circle if the central angle of 3 pi over 2 intercepts an arc of 26.4 centimeters. Okay, so now we have our central angle, our theta, equal to 26.4 centimeters, and we don't know the radius. So we would have to multiply both sides by radius, and we get 3 pi over 2 times radius is equal to 26.4 centimeters. Then we need to get rid of this. Remember, when we have a fraction times our variable, to get rid of it, we multiply by the reciprocal. So we're going to multiply both sides by 2 over 3 pi. Okay? Those cancel, and then our radius becomes, let's take a look here. I hope you can see this on the calculator, 26.4 times 2 divided by, okay, so we don't want centimeter, or we don't want pi on this one. They're not looking for an exact answer here. So divided by, I'm going to use parentheses and my little pi button. And my answer is 5.60, but I'm going to go ahead and round it, 5.6 centimeters. And that is letter C. All right, let's take a look down here at problem number 32. A circular gear turns 60 degrees per hour. How many radians does it turn in a 24-hour day? First, let's change our 60 degrees into radians, right? So we're going to multiply that by pi over 180 degrees so that our degrees cancel. We're left with 60 pi over 180. We can cancel out the zeros. Whenever two numbers have, well, it could be more than one. Whenever they have matching number of zeros at the end, you can just cancel them out. And then this reduces to pi over 3. Now, that's in 1 hour, and we need 24 of those. So we're going to multiply this by 24. We will reduce, and so we end up with 8 pi radians per day. Letter C. Okay. This next one, number 33. The propeller of an airplane is 9 feet in diameter. What is the speed? All right, so 9 feet in diameter. What is the speed of the tip of a propeller blade if the angular velocity of the propeller is 50 radians per second? Okay, remember on the page before this that the velocity is equal to omega, or the angular velocity, times the radius. Okay, that's the formula that we're going to use here. And so we have 50 radians per second times the radius. Our diameter is 9 feet, so 4.5. Okay, and 50 times 4.5 is 225 feet per second. Okay, which is answer C. All right, let's do one more together here at the top of page, what is that, 71. A wheel moves with an angular velocity of 16 radians per second. I'm going to just start marking these 16 radians per second with their symbol so that I know what's going on. It says find the speed of the wheel, so we're looking for V, if its diameter is 28 inches. So the radius is equal to 14. So V equals omega times the radius. So I have 16 times my radius, which is 14, which is 224 radians, or sorry, what are we at? Inches per second. 224 inches per second. Okay, so page 69 has those formulas. They will be useful to finish these problems out. That's it for this section. That's it for Unit 3 altogether. As always, if you have any questions, do not hesitate to contact me. I'm happy to help with anything. I can put together mini video to go over some problems. Otherwise, until next time.